Hey, welcome to chemistry. Today we are going to discuss Charles's law. What's Charles's law? Well, Charles's law is the relationship between volume and temperature. Now, we talked about temperature before. We said that temperature was the average kinetic energy of the particles. And we also stated that that really meant that's how fast the particles were moving. As the temperature goes up, the particles move faster. As the particles move faster, they need more space. They need to spread out. Charles' law. It's a direct relationship between temperature and volume. As the temperature gets higher, the volume also has to get bigger. All right. Now, we have to talk about temperature before we can do this. Actually, the temperature scales. Now, we're familiar with at least two of the three temperature scales, Fahrenheit and Celsius, but we also need to talk about Kelvins also. So let's get down to this real quick. First of all, let's look at Celsius and Fahrenheit. Celsius and Fahrenheit, Fahrenheit was named after the man who invented the mercury thermometer. And when he made his new thermometer, he just put lines on there, marks on there, right? And that became, wherever the numbers lay or fell, that became the scale. And it just so happens, if you can look over here to the side, that water freezes at 32 Fahrenheit and it boils at 212 Fahrenheit, right? Not very practical numbers, but it's just random happenstance. Now, a guy named Celsius comes along, and his big plan was to make it centigrade, which means 100. 100 what? 100 degrees between the freezing point of water to the boiling point of water. Now, when he made his original scale, he called boiling 0 and freezing 100, which is upside down. So scientists quickly changed that around. So 100 higher energy was a higher number, and freezing, which is lower energy, was a lower number. So just make sure that that's the idea behind the two scales. All right, now the third guy, Kelvin. Kelvin realizes there's something fundamentally wrong with this scale. And that thing that's fundamentally wrong with the scale is down here, below 0, in the negatives, right? Because this is a measurement of energy. We cannot have negative energy, right? If it's moving, it has energy. If it stops, it has 0 energy. It can't then go backwards and have negative energy. Just can't happen. All right? So Kelvin's idea was to stop the scale at 0, where the energy is 0, where there's no motion. So he takes and he graphs out a bunch of information about speeds of particles and energy, and he notices a correlation where they all seem to be pointing at some mysterious point way off the scales, which he hypothesized was absolute 0, where all motion stops. Now, if we had to go down to that on our Fahrenheit scale, it'd be negative 460 degrees Fahrenheit. If we had to go down on our Celsius scale, it'd be negative 273 degrees Celsius. Very chilly, right? The chilliest. It's the coolest number there is. So he made that his absolute 0. Now, he also used Celsius's scale. So he used Celsius scale. He just slid the 0 down to where it was actually no energy. And so you'll notice as we go from negative 273 Celsius to 0 Celsius, the Kelvin scale goes from 0 Kelvin to 273. Another 100 up, 373 is where water boils. So he's using Celsius scale, which makes it easy for conversions for us. And so conversion-wise, I have these written on here already. Conversion-wise, all we have to do is add 273 to the Celsius to make it into Kelvin. Simple as that. Now, because this is a relationship between the true energy and the volume, you have to use kelvins every single time in gas laws, because we're measuring the energy of motion of those particles, and we need to have the true scale, the scale that starts where 0 is 0 motion. Okay, keep that in mind. Okay, now let's do some of these problems. They're pretty easy. I think I already have some on another slideshow. I'm going to knit this together, so if I overlapped, I'm sorry. For Charles's law to work, we have to be in kelvins. So we're going to do the same format that we had before. We have our givens. We're going to list our givens just like we did before. So a container holds 50 milliliters of nitrogen at 25 degrees Celsius and 736 mmHgs. What will be its volume if the temperature increases by 35? So we threw in some extra information here that we don't need, because there's no pressure, there's no second pressure. So we're not going to say that the pressure is going to stay constant. We don't need to list it. So let's get this in the right spots. So I'm going to call V1 50 milliliters. T1 is 25 degrees Celsius. We do not need the pressure there because it doesn't really ask for it. What will be the new volume if the temperature increases to 35 degrees? All right, and we're looking for the new volume. All right, so there is the given. Now, again, we have to make sure that we have consistent labels, and we have to make sure that temperature is in Ks. So let's change those temperatures, add 273. And so that should be 298, and 273 plus 35 should be 308. All right, and we're solving for V2. Now, the formula is not the same as Boyle's law, right? This is going to be a direct relationship. So we have V1, T1 equals V2 over T2. So we have V1 over T1. All right, so we're going to use the same idea as we did before. When we want to isolate the unknown. And so we're trying to find V2. So this time, T2 is on the bottom of that fraction. So I'm going to take it and I'm going to move it across the equal sign to the top of the fraction. All right, I'm crossing it, multiplying, cross-multiplying. All right, and then I end up with V2 equals T2 V1 over T1. All right, and now I'm going to sub in my numbers. So make sure you get things in the right spots. Make sure that you use your new adjusted temperatures. Remember, when you're putting this into your calculator, make sure that you multiply the tops, divide the bottoms. So in my calculator, I'm putting 308 times 50 divided by 298. And I'm getting 51.7. And that would be milliliters. Okay, what happened? The temperature went up, the volume also increased. Direct relationship. Now, that wasn't a very big temperature change, so it wasn't that big of a volume change, right? Okay, now solving for temperature. We're going to follow the same things that we just did. Let's get this down. Calculate the decrease in temperature when 6 liters at 20 degrees Celsius is compressed to 4 liters. We're trying to find this next temperature. Again, labels are consistent, liter, and we have to make sure that we have this changed to Kelvin. So that's 293. Okay, now when we're solving for temperature, look at our equation. I have it down here so we can see it. All right, I have V1 over T1 equals V2 over T2. We want to solve for the T's. The easiest thing to do is to flip the whole equation over. So the thing you're trying to solve is on the top. All right, it'll just make your algebra easier. So I'm going to put my T's on top. So T1 over V1 equals T2 over V2. Now by doing this, it's going to simplify my algebra. Now I want to get V2 by itself. T2 by itself. So what am I going to do? I'm going to lasso my V2 and I'm going to move it up. And I can put a 1 down here if you want. It depends on what kind of person you are. All right? And now I have it set up in the correct form. Make sure that you solve for T on the top of the fraction. Don't solve for 1 over T by accident, or you're going to end up with the inverse of the answer, which we don't want. If you get a very small decimal point, 002 something, it's probably wrong. It's probably your algebra. You probably have the thing flipped upside down. All right, enough said. Let's just punch this in. So we have, 293 times V2, which was 4, divided by 6. And I end up with 195. Okay. And it did decrease, which is a good sign. All right? Those are Charles's law. So make sure that you follow the law. Make sure that you use our equation, and you can flip it upside down if you need to. If you're solving for T, just flip it upside down. And most importantly, don't forget to change it into Kelvins. All right. I got to try to edit this mishmash of stuff I have together into something that makes sense. Too many technical difficulties in this today. So have a great day.